All right. So, welcome to Lecture 10, the second part of our TFL Natural Deduction lectures. What we're going to do today is actually fairly straightforward. I want to talk to you about some proof-theoretic notions. So notably, these proof-theoretic notions are paralleled by semantic notions that we defined up in the first block of the course. So in particular, what I'm going to give you today is going to be semantic notions that parallel all of the tautological concepts that we defined in, I think it was probably lecture 3. So if you remember, we had concepts like being a tautology, being jointly tautologically consistent, being tautologically equivalent. We're going to have parallel concepts defined today. But of course, all of these parallel concepts aren't going to be defined in terms of valuations, like what we had before. But instead, they're going to be defined in terms of proofs in our natural deduction system. So that's going to be the big part, right? We're going to talk about these proof-theoretic notions. And obviously, one of the things we can do is we can use our natural deduction system to track these proof-theoretic notions. So I'll tell you a little bit about how we can use the natural deduction stuff we've been talking about to do that. And then I'm going to spend 5-10 minutes talking about proof strategies. Now at this point we have 1 week's kind of experience talking through how these proofs go. And one thing to say, they're hard, right? If you've never done this sort of thing before, it can be kind of weird. Especially if you're just not familiar with the format, the idea. The nice thing is, it's also very regimented. It's not mechanical, so it's not as simple and straightforward and literally like algorithmic as it was with truth tables, but there are some things you can do to kind of make your life a little bit easier. So that's what we'll talk about in section 2. And then in section 3, which will be the second half of the lecture, we'll go through some sample proofs, and we'll talk through how to use our natural deduction system for TFL to track our various proof-theoretic notions. Sounds good? Beautiful. All right. So let's start by talking again about these proof-theoretic notions. The first thing to start is going to be our single turnstile. Notably, the single turnstile is, as the name suggests, the single turnstile. It's not the same one that we saw before. The one that we saw before in the first block was the double turnstile. The single turnstile expresses provability effectively. It's going to say, hey, there's a possible proof. So notably, our single turnstile is intimately bound up or related with the double turnstile. But again, they're fundamentally different notions. As we indicate here, right, if we're thinking about TFL, the double turnstile is effectively defined in terms of valuations, right? Assigning truth values to atoms. And it tells us something like tautological entailment, if we're thinking of TFL. The single turnstile, not that, right? It's literally, it's possible to prove using the natural deduction system. So importantly, again, they are different concepts. So to say A1 through AN, single turnstile C, that tells us that there is some proof, or there's some possible proof, that starts with A1 through AN as assumptions, and ends with C. You've been doing this already. Right? We've been writing it down as kind of an argument with a little therefore symbol, right, the 3 dots, but we could have been writing it with this single turnstile instead. It just tells you, hey, you can start a proof taking A1 through AN as your initial assumptions, draw your assumption line, and then you can construct a proof using the rules that ends with C. Similarly, if we have the line through the single turnstile, it's telling you, hey, there is no such proof. I'm going to tell you something really interesting right now. Within the natural deduction system, within the kind of game that we've been talking about the last 2 weeks, there is no way to show that there is no such proof. You can never show that there's no possible proof. And that kind of makes sense. It's a little bit like a language trying to tell you what the language cannot say. If there's something that is literally inexpressible in English, I'm going to have a really hard time telling you about it right now. Here's what's inexpressible in English. Cool, very communicative. You see the problem, hopefully, right? This is a system designed to do one thing, build proofs. What it cannot do is show you that you can't build a proof. You need to step up and think about it outside the system. And that's fine. That's not really a bug, right? This is just a tool that can be used in various ways. It's a limited tool. That's all right. But what we'll be able to do is to show that the provability holds, because you can literally just build the proof. So there's our first notion. This single turnstile tells us provability. Now, in light of this single turnstile, we'll be able to define up a bunch of properties. These will be properties that individual sentences have, that pairs of sentences have, or that groups of sentences have. And these are going to parallel, well, here's an interesting question, right? We'll talk about the first one. So here's our first notion. Our first notion, an individual sentence of TFL is a theorem if and only if there's a proof for that sentence starting from no assumptions at all. So to show that a sentence is a theorem, you can start a proof, right? You draw that assumption line. You draw the assumption line, and your first numbered sentence is below the assumption line. If you can do that and derive the sentence as your last step, then you can prove that the sentence is a theorem. So here's an interesting question. What concept does this parallel? What's the kind of truth table defined or valuation defined notion that being a theorem is very closely like? Yeah, exactly. Right? A tautology. So if we remember, being a tautology is a TFL sentence that's true in every valuation. To be a theorem, you literally depend on nothing. You can be bootstrapped into truth from literally no assumptions whatsoever. So something we're going to talk about in just a second is how these two concepts end up perfectly lining up. So we can use our natural deduction system to show that a sentence is a theorem. And the way that we do it is we offer a proof for it starting from no assumptions whatsoever. So I'm going to go forward a slide. We'll come back in a second, right? Here's an example. I'll show you a proof for a sentence that's a theorem. So we take, in this case, nothing as an opening assumption. Notice that there's literally no numbered sentences above the assumption line. Instead, the first sentence, the first numbered move in the proof is below it. And also something noticeable as a little friendly tip. When you're proving theorems, 99.9% of the time, the first move you're going to have to make is opening a subproof. Because it's really hard to have nothing to work with. So in this case, we open a subproof, and our aim with the subproof is eventually to do negation introduction. And what we show in this case is that what we often call the law of non-contradiction is a theorem in our system. That is, if we had a sentence A and its negation true at the same time, we'd get a contradiction. So based on negation introduction, we know that that can never be the case. Now, if you remember, this is actually a deep, dark assumption that we took way back in, I think, lecture 1 even. 1 or 2, I don't remember exactly. But note that our natural deduction system can prove that this is the case, which is handy. It's almost like it was made to do that. Interesting. But again, what we can do, if I give you a sentence and ask for you to show me that it's a theorem, you should be able to construct a proof for that sentence, starting with nothing at all. We'll do an example of this in the second half. But again, do we see the broad idea? So what's interesting, to go back a slide, what's interesting is while our system can show that a sentence is a theorem, it is not capable of showing that a sentence is not a theorem. I've said it's very difficult. That's me being very nice. The natural deduction system alone cannot show you that a sentence is not a theorem. Again, this is kind of parallel with showing you that you could not build a proof. The system can't do that. What do you think we would do if we were going to show that a sentence is not a theorem? What tool could we use? Nice! Right? We can construct a truth table. If we can construct a truth table, and there's even one valuation where the sentence comes out false, then we know it's not a theorem. It depends on certain atomic sentences in these cases being true in order for the sentence itself to be true. So, okay, we have our first proof theoretic concept, being a theorem. One thing to note, get this little bit here. So if I give you a question, say on the exam, something like this, what I'm asking you to do is show me that the sentence on the right is a theorem. There's literally nothing to the left. So you start your proof assuming nothing and end with this sentence. Cool? Make sense? Again, conceptually, that's the important thing. We'll talk about how to do some examples of it as we go along. So let's talk about our second concept. The second concept is a property that will hold between two sentences. We'll say two TFL sentences are provably equivalent if and only if each can be proved from the other. That is, you can construct a proof starting with A that ends in B, and you can construct a second proof that starts with B and ends in A. So literally, that. You got to have both. So what's the parallel concept to this? What's the semantic notion that this is tracking? So if we think back to the stuff defined in terms of valuations, what property is this very similar to? Close, close. Anybody help him out? So I asked you to actually check for it on the midterm. Let's think. The clue's in the second word. Equivalence, right? It's tautological equivalence. This is our parallel to tautological equivalence. But it's our provability parallel in terms of tautological equivalence. What this is showing is that whenever A is true, B is also going to be true, and vice versa. So another kind of question to ask here, if I give you one of these, if I say, hey, here's two sentences, show me that they're provably equivalent, how many proofs do you have to give me? If I give you two sentences and I ask you to show me they're provably equivalent, how many proofs do you have to give? Two. Got to give two, right? You got to give me one starting with A and ends in B, and a second one that starts with B and ends in A. So again, I'll give you an example. It's just a kind of easy example. We'll go forward a slide. A very silly one, but it's a convenient one. So we have G and not G. To prove these are provably equivalent, we start one direction with the left sentence and derive the right. That's our proof on the left here. And for the other way around, we start with our right and derive the left. Again, easy peasy. So notably, that means that in the final exam, these questions are worth twice as many points. Because, you got to do two proofs instead of just one, like all the other questions. But again, the general idea here, to show that pairs of sentences are provably equivalent, I'm going to go back a slide here. What we got to do is give me a pair of proofs. One that starts with the left, ends with the right. One that starts with the right, ends with the left. So far, so good? Now, an interesting limitation of the system is that it cannot show you that two sentences are not provably equivalent. Again, this is kind of parallel to the other limitations that we mentioned earlier. So, we can show that a sentence is a theorem. We can show that two sentences are provably equivalent. So one last kind of proof theoretic notion to talk about. We can show that some sentences, A1 through AN, could be one sentence by itself, could be 2, 3, 5, 50, whatever. Some sentences are jointly contrary if and only if we can prove a contradiction from them. So what we do here is we take the sentences as assumptions, right? Open our proof with them, and then we end in a contradiction. So, interesting follow-up question. What's the concept that this is parallel to? What semantic notion is this tracking? Well, let's think, right? If it turns out that... Go ahead. Yeah, it's showing tautological inconsistency, right? It's basically showing, were they all true? Let's assume they're true. What happens? We end up in very bad stuff. If A1 through AN are true, we get a contradiction. So they must not all be true together. That's effectively what this is doing. So nice, that's kind of cool. Interestingly, just like with the other problems, or limitations rather, I shouldn't really call them problems, our system cannot show that sentences are not jointly contrary. Again, it's the same kind of thing, right? We can't show that these ones taken together definitely don't lead to a contradiction, because there's an infinite number of potential moves that might go on later. So as an example, here's a very silly but very simple kind of proof for joint contrariness. We have three sentences at the top, a conditional, and then the negation of the consequent of the conditional. We very quickly get a contradiction. Cool. What we can conclude is that 1, 2, and 3 are jointly contrary. Don't really say anything else. We just conclude that these sentences taken together cannot all be true. So what I want to try and do in this second half is to go through at least one of each type of question. Again, kind of working through making sure that we're all on the same page. But what's important is that we understand the concepts, right? We have proving a sentence is a theorem. We have proving pairs of sentences are provably equivalent, and we have proving that some sentences are jointly contrary. These are the three kind of proof theoretic properties we're going to track. What's noticeable? Two things, I guess, noticeable here. The first is to show that a single sentence is a theorem, one proof. To show that two sentences are provably equivalent, two proofs, right? A to B, B to A. To show that some sentences are jointly contrary, one proof that takes them as assumptions, ends in a contradiction. What we're missing is all this stuff. Now, when it comes to TFL, we already have a tool that lets us do both of these. The tool we have for TFL was truth tables. They're beautiful, they're lovely, they work really well. But here's the really cool thing. Think about FOL for a second. Remember how in FOL there was a bunch of stuff we couldn't do. We couldn't show that two sentences were logically equivalent. We couldn't show that a sentence was a logical truth. We couldn't show that an argument was valid. If you remember, interpretations only let us show, in this case, kind of negative aspects. This sentence is not a logical truth, not a contradiction. These sentences are jointly consistent. This argument is invalid. The natural deduction system is starting to fill in the gaps. For TFL, there were no gaps to fill. For FOL, though, this is where it's going to really hit its money. Because everything interpretations couldn't do, natural deduction can. But of course, right, if we're just focusing on TFL for now, which is what we're doing today, the natural deduction system's pretty limited. It can only do half as much as the truth tables could. But again, we still get some gain, because the natural deduction system shows us the path of reasoning. It shows us how you can go from some assumptions to the conclusion, or how these assumptions lead to a contradiction. Something that the truth tables just didn't really give us. So to kind of wrap up this section, come back again to these two fundamental notions. We have the single turnstile and the double turnstile. The single one, again, tells us provability. The double turnstile, if we're thinking about TFL, talks about valuations. And it's worth stressing again, these are fundamentally different notions. The double turnstile is deeply concerned with the truth or falsity of the relevant sentences. And we can talk loosely about truth or falsity with our provability, but note that that never really enters in. We're only thinking about syntactic manipulation. We talk about assuming as true, but that's just fast and loose. But the really, really cool thing, and this is why we'll be able to do what we can do when we get to FOL next week, is that despite the fact that these two notions are fundamentally different, there is a beautiful and intimate connection between them. And the beautiful and intimate connection is that they are extensionally equivalent. That is, provability holds if and only if tautological entailment holds. And the same is going to be true when we move to FOL. Provability for FOL natural deduction perfectly lines up with logical entailment for first order logic. This is a huge payout. Because what it means, again, to stress something we're going to talk about next week, basically, is that our complete logical system is going to be, when we get to FOL, for the stuff we couldn't do with interpretations, we can do with natural deduction. For the stuff we can't do with natural deduction, we can do with interpretations. Together, we will have a complete logical machinery. So, the kind of neat upshot of this extensional equivalence is that we can say premises tautologically entail the conclusion if and only if we can prove the conclusion from the premises, take them as assumptions, derive the conclusion. Two sentences are going to be tautologically equivalent if and only if they're provably equivalent. And sentences are jointly tautologically consistent if and only if they're not jointly contrary. Again, for TFL, fine, we already have truth tables that do everything. And when we get to FOL, we'll be able to replace all of those ones on the left with the non-tautological versions, the non-truth functional versions. That's where the big money's going to be. But we got to get through this. Practice with this first. So, the big point to stress, right? Single and double turnstile, fundamentally different notions, even though they're extensionally in agreement. Okay. So that's the kind of general introduction, not introduction, that's the whole bit, for the proof theoretic notions. We have showing a sentence is a theorem, we have showing pairs of sentences are provably equivalent, and we have showing that some sentences are jointly contrary. In the second half, we'll work through a couple examples of each one of these to make sure we're all on the same page. Before I move on, I want to pause and ask, what questions do you have for me on these? What questions do you have for me about these sort of proof theoretic notions?
Could you repeat the term of jointly contrary?
Absolutely. We'll go back. So, again, the general idea is that some sentences are going to be jointly contrary if we can take them as assumptions and then derive a contradiction from them. So thinking in terms of our proofs, what we'll do, we'll take some sentences and then we'll take them as our initial assumptions, and then no matter how many steps it is, our proof is going to terminate in that upside down T. Again, we'll work through a couple examples in the second half to get a grip on it, but that's the sort of questions we'll do, right? Give you some sentences, and you'll show me that they can't all be true together, because if they were, bad stuff. Any other questions? Before we go on, again, do we have a kind of grip? Do the general concepts here, are they clear? There's both in terms of like what they are, and then also how we can do it. We're going to go through some examples. That's what we're going to talk about in the tutorials as well. So don't worry if you don't quite have a grip on how to prove it yet, but that's what we're going to do. So, in that case, let me talk about some general proof strategies. And here I'm going to be extremely vague and extremely general. Because put really bluntly, it would be lovely if natural deduction was mechanical, if it was algorithmic. It's not, really. And that's a shame. Because then it's slightly harder to teach, and it's harder to do. But I can give you 3 general kind of suggestions about how to approach constructing proofs. And this will be the case for any kind, whether you're proving provable equivalence or joint contrariness or theoremhood or just proving that an argument's valid. So the first one is one we talked about in the tutorials. The first suggestion that I can give you, and this is honestly probably the best advice I'm going to. Because put really bluntly, the hardest thing with these is to get started. You write the sentences down and then it's just like, well, what the fuck do I do now? I have no clue. So here's some advice. Step back, start planning. And the first move in your plan is to think about the last step you will make. Work backwards. You know where the proof needs to end, right? It needs to end with a relevant conclusion. So think about what rule you're going to use last. If it's a sentence that's got an operator, think about the introduction rule for that operator. Right? If it's a conjunction, cool, it's probably going to be conjunction introduction last. If it's a negation, it's probably going to be negation introduction. And then that will help you start to plan what you're going to do in the proof. As you get your first idea, right, about the last move, then literally move to the penultimate step, the one just before the end. Think about, cool, what rule am I going to use to get this sentence? And so on and so on and so on, until either you've worked your way all the way up to the top, or the pathway becomes clear. Again, this is advice. It's not always going to work, but it's a handy place to start. The second bit of advice I have, it's going to sound almost paradoxical, but actually it works very well in tandem, is work with what you've been given. That is, look at your assumptions. Think about what the main operators on your assumptions are. Think about what kind of rules you can apply to them. Do you have a sentence that looks like this? If you see a sentence that looks like this in your assumptions, what rule does this immediately suggest? Does anybody have any ideas? De Morgan's, right? If you see something like this, think about, cool, what happens if I use De Morgan on it? Right? I get something that's much more usable, because conjunctions are easy to break. You can get parts out of conjunctions, right? Again, this is advice. It's not always going to work. But think about the premises that you're starting with. What kind of rules can you apply? What sort of stuff can you get out? This works very, very well with the previous bit. Start off by thinking about what your last move is going to be, because that will help you figure out what the big move in the proof is going to be. This will help you figure out how you can get the parts. Not always, but it's useful. The third bit of advice I have is something we haven't really done yet, but it's worth thinking about. And this is constructing proofs that are indirect. So what we do to prove something indirectly is we assume its negation. So we open a subproof with the negation of the sentence we want to get. So you might start, if you want to get A, we'll start a subproof with not A. And the idea is to eventually show that this leads to a contradiction. And the reason is because we can then close a subproof and get not A. And that looks backwards, but no, what can we immediately do for not A? We can quickly do D and E to give us the result we want. So proving something indirectly, you assume it's false, speaking metaphorically, you assume it's false, you show that it being false leads to a bad problem, leads to a contradiction, so then you conclude it must be true. Now this sort of method of indirect proof, sometimes it's very easy, sometimes it's actually not possible, sometimes it is the only way to go. But this is, again, the general kind of thing here, right? It's a bit of an art rather than a just pure mechanical method. Yeah.
So what would be the main thing, like in the not in the subproof, but in the main?
Good. So the main proof would basically, the main proof line would be like here.
Yeah. And what would be on top of it? Nothing?
I mean, depends. So I was trying to keep it very abstract here. The general kind of move that you would make. So there could be a bunch of assumptions. In fact, there's very likely to be a bunch of assumptions, right, to allow you to derive this contradiction. So this is very, think about these as in my sexy swatch font, And what I'm trying to do here is just give you a version of something like a rule. So yeah, this could be plugged in if you're proving a theorem. This could be plugged in if there's a ton of assumptions and we're playing around here. These sentences could be any kind of sentence you want. Again, it's just kind of describing the general method.
Yeah.
Okay. Yes?
So, did you prove that A is a theorem here?
Good. So, I mean, if this worked, if it worked, yes, we'd be proving that A is a theorem. In this case, assuming that this is like our first sentence and this is our last one. Again, the kind of, don't get caught up in the example too much, is just the generalization idea. But yeah, good. Okay. So, again, these sorts of 3 bits of advice. Start from the back. Think about your last move because it gives you a plan. Secondly, think about the toys you have to begin with and what rules you can apply. And lastly, think about this idea of proving something indirectly. It's another way to go. Yes, sorry.
How would that prove it's a theorem? Like, I think it is on the...
Good. So in this case, I mean, again, we're kind of thinking about it hypothetically. This would prove it's a theorem if the proof was successful, because we're assuming nothing. There's nothing kind of above the assumption line. Instead, we're starting below the assumption line. Again, hold the thought. We'll come back to proving theorems in the second half. There is one last bit of advice I want to give you. And this isn't really a kind of suggestion about what to do or how to do things, but just a general bit of advice. Ooh, which is just don't give up. Right? Just keep trying. There's several reasons to say this. One of them is, right, every natural deduction proof is worth 2 points when we come to the final exam. Some of them are worth 3. The really complex ones at the end are worth 3. Notably, if you just do some of it, you can get some of those points. If you kind of get through most of it, but you don't get the right answer, I can still give you a point. If you're on the right lines. So again, don't give up. Just keep working it. Also, relatedly, if I give you one that's not provable, which, you know, it happens amazingly, I am not perfect, right? If I screw up and give you a question that's unanswerable, points for free, because it's on me. Right? I hope I don't do that. But again, what I mean here is just keep trying. Just keep trying. Keep thinking about it. Keep planning. Keep playing around. There's very likely a way to get there from here. So even if you're stuck, cool. Then take a step back and think about a different way to go. Okay, so that's the content that I wanted to cover today. It's not a whole lot of new stuff. It's basically just thinking about these semantic concepts. Sorry, shouldn't say semantic. Our syntactic concepts, our proof-theoretic notions, being a theorem, provable equivalence, jointly contrary. These are 3 kinds of concepts that we'll now be able to track using our natural deduction system. So what I'd like to do now, we'll take a little break. And when we come back, we'll talk through at least one, if not more, of each type of proof-theoretic property we can track. Okay? So we're at, 26. So let's come back in 10 minutes at 36, and we'll talk more about how to do these. Okay? Cool.